Hello, everyone, to this Spring into STEM lecture. So my name is Adnan Mehonic, and I'm a lecturer in nanoelectronics here at EEE department. And what I'm going to talk about is the future of energy efficient AI. So this is a very timely, interesting topic with a lot of potential solutions and many different techniques that we could use to improve the efficiency of AI systems. So what I will try to do is actually to paint a big picture first, and then to present one particular solution, which is the solution that I've been working on in EEE for many years now, and that's memristive technology. I guess I don't really need to convince you that AI today is huge. We do use AI techniques for a very wide range of applications. And what's even more interesting, that the range of applications where we can apply AI is expanding all the time. So we'll read in the mainstream media that AI is applied for these kind of applications, but then some applications that we are not even considering today. What is, to me, very inspiring and quite profound, that we are at this stage where AI is applied not only on these what we can class as simplistic applications, but also to do the scientific discovery. So this is the recent example from the DeepMind's system called AlphaFold that was able to solve large complex problem in biology. That was an open question for more than 50 years. And by opinion of many experts, this discovery might lead to winning a Nobel Prize. So if not in this particular case, it is, I think, inevitable that the future Nobel Prize awards are going to be given to discoveries made by using AI techniques. So we have all motivation and the reasons to carry on with development of artificial intelligence. But here is the part of the story that you might not hear that often, is that what are the hardware and power requirements when we are using AI today. Especially this is the case when we are talking about the complex algorithms that are very useful. So this is probably the most famous AI system, AlphaGo, that was able to be the human champion in this very creative game. But now pay attention to the resources that we need to run such a systems. We are talking about thousands of CPU units, GPUs, hundreds, and then in terms of the power, consuming something of order of megawatts of power. So then, okay, let's now think about the trends and if this is really the reason for concern. So what you're seeing on this graph actually presents how the computing power demands increased over time. So on this graph, you can clearly see the two eras. So basically one era till 2012, where the compute power demands would double every 24 months. So you're aware of Moore's law, and we had no issues with basically meeting that demand. But then since this wide range mainstream boom of AI applications, we can now see that doubling happens every 3 or maybe even 2 months. So that's a big challenge for us. We should recognize that we managed to improve the performance of AI hardware over the last couple of years significantly. And this is not only thanks to the Moore's law, because the Moore's law has been slowing down significantly over the last few years, but actually smart architectural solutions. So this is the example from NVIDIA. And you can see that over the last maybe 7 years, the performance have improved by a factor of 300. But the challenge and the issue is that over the same period of time, the compute power demand increased by a factor of 300,000 times. So here is maybe the most striking effect of that, and that this another graph is representing the cost of training state-of-the-art AI systems. So we can see that back in 2012, where we all kind of started with AlexNet, it would cost something like a couple of dollars to actually train such a system. But these days, when we are talking about very complex natural language processors like GPT-3, that costs of order of tens of millions of dollars to train. So this basically is the story about how we basically have this huge demand and the current hardware is not able to supply it. So here are the ways to improve. So basically, we have still Moore's law, although it has been slowing down. And even if we are to carry on with the Moore's law in the future, which is going to be impossible, the type of the improvements we are going to get are not enough. alone to basically meet this demand. The other sort of game that you're playing, and this is the main game, is to rethink about the design of the computer architectures and chip design to actually improve the efficiency. And then in parallel, we also have to scale up these systems. So we are building more data servers, more data farms where actually computing takes place. So here are again some trends. So again, and this is almost outdated graph now. It shows you how the Moore's law has been slowing down. Also something called Dennard's law related to the efficiency of transistors that we have has pretty much stopped maybe 15 years ago. And now these architectural solutions are reflected in this graph number of cores. So that's kind of the optimization that you're using. So I did mention there is a parallel approach that you just scale up the whole thing and building more data centers. Well, that kind of works. We're using cloud computing, but the whole approach might not be sustainable. We might get to the regime where using way too much energy to run other data centers. And these data centers are not really environmentally friendly because we produce a lot of carbon footprint just by training these large networks. And there's the whole other range of the applications where the cloud computing might not be ideal. So we have what's called edge computing, where we would like for computing to take place on the local devices. And there are many compelling reasons why we would like to have that. So it could be related to privacy of the data that we send, latency that could be quite restrictive for particular applications, and also infrastructure. You know, if you are in London Tube, that your smart assistant doesn't work because you're not actually connected to the internet. So this is what has been happening and what is happening now. We still do rely on the digital electronics and the current CMOS technologies. And we are basically trying to co-optimize hardware and algorithms so we can improve the energy efficiency. And this is basically, you will see that we are now sort of talking about reduced precision computing, which is very applicable for AI. And that might bring us a couple of orders of magnitude in terms of the energy improvements, energy efficiency improvements, but ultimately we might need to have something new, something else. A very important point is to actually understand where does this inefficiency comes from. And basically it comes from the fundamental architecture design of our current computer chips or computer systems, I should say. So computer systems are based on what's called Voigt-Neumann architecture that sees a very clear differentiation between the memory units and the compute units. And actually, when you do the analysis where the energy is spent, the computing is relatively cheap, but whenever you need to move the data from memory or to compute unit, this is actually where this energy consumption goes up dramatically. So we'll see like doing additions and multiplication doesn't cost as much, but then when you fetch the data from on-chip or especially off-chip memory, this energy goes up dramatically. So historically, we had a lot of different architectures. So these are the main ones trying to address this issue. So currently we have a GPUs, which is sort of mainstream for AI, but a lot of interesting development around ASICs, specific chips and circuits to address the workloads related to artificial intelligence. Now, what I've been working on, and we at EEE department, is really try to tackle this problem at the more fundamental levels. It's really to start to think about how we can make and design the basic computational units to then build from there our AI hardware systems. So any future technology would need to deal with these challenges. So there's Moore's law, there's memory wall, there's heat wall. And one technology, which is not CMOS technology, it's memoristic technology. So technology that I've been working on, and memristors as a concept have a very rich and interesting history. So they've been introduced as the concept some 50 years ago, more than that now, as the fourth passive circuit element. But what is practically interesting and important for us that maybe over the last 10 years, we've seen, or more than this now, maybe 15 years, we've seen many different implementations of memoristic technologies. And they typically have this very simple structure that looks like basically like a capacitor. So it doesn't really get much simpler than that. But they have one very special and very useful property that the resistance of this element of this memoristor can be changed dynamically and very efficiently. So this is appealing for many different applications, but one of them is, of course, memory. So for the maybe solid state physicist or material scientist in the audience, this is how one kind of memristor could look like and how it could work. So this is basically the cartoon of the physical processes that are driving the operation of such a device. So we have, as I said, this capacitor-like structure. So we have 3 layers. These are just the metals that are in most cases passive. What you have in between is this switching medium that in our case is oxide material, but it could be something else. And then this is nominally an insulator, something that wouldn't really conduct very well. But if you apply the voltage across the terminals of this device, it is actually possible by using the electric field to extract some of the oxygen from this oxide matrix. What is left is what's called filament of oxygen vacancies. And as that happens, when you produce these conductive channels, your device goes from the insulating state to the conductive state. The most important thing, this is a reversible process. So you can actually push this oxygen ions back into the conductive filament, and you can reoxidize the parts of the filament to retrieve the high resistive state. So you can then go from the low resistive state and high resistive state, and this is very, very useful. It could be used as a binary switch between the 2 resistive states that are now representing zeros and ones, but also many intermediate states are also possible. So then let's see how does it behave as a memory. And because it's non-volatile memory, meaning that it retains the state even when you turn off the power, the natural comparison is against current state of the art, that's flash technology. So you can see on these many figures of merit that memristors do beat flash memory almost in all of them. And a very direct benefit of that is to actually use memristor technologies for something like embedded memory with the microcontrollers today, because actually the flash that we currently have is not compatible with the most aggressive processing nodes. So that's quite interesting. You can actually get much more powerful microcontrollers, so all of those devices that are sitting somewhere near the sensors or at the edge. We can think about your, I don't know, Fitbits or something like that. All of this could be quite useful. But the other part of the story, which is even more interesting to me, is how we can use these devices not in a digital way, but in the analog way. And by doing that, we can do something very useful, which is do linear algebra in a very efficient way. So why is this relevant and important? Because all current machine learning algorithms are basically could be broken down to doing linear algebra in a very, very efficient way. So memristive devices are actually very well suited to do this kind of operations. This structure that you see in here is what's called crossbar array. And you can actually, by applying the levels of the voltages and sensing the currents, you can get a very nice or very efficient multiply and accumulate operations. And it's not only that you are sort of using the fact these are now the analog devices, so you can pack more information than in a single bit, but also this is what's called in-memory compute. You don't need to move data anywhere. The processing is done directly in memory. So you're basically breaking down this von Neumann bottleneck that you have. And that results in a huge benefit in terms of the energy efficiency. You can also think about this in terms of just looking at these memoristic devices or their conductances as a proxies for the weights in your artificial neural networks. So this is a very direct way to actually connect your hardware to software and to do a lot of useful optimization. And yeah, so this actually could be used for the NNs in a very, very direct way. Now, I gave you like a high level picture why this could be useful, but here are some concrete figures. So we can see there is the computing performance compared to the current state of the art. And with this, the approach, which is this yellow line, you can expect to get a couple of orders of magnitude improvements over current state of the art. So that's very, very useful. Now we need to be a bit careful with this approach and how scalable it is. It is good to have novel computing units, these memoristic devices, but ultimately we really need to think holistically about the system design. One very remarkable fact about the biological systems is that the energy consumption of the brains of the different species scale linearly with the number of neurons. So for example, if you have the certain species that has twice as many neurons, the energy consumption goes linearly. But then with our current hardware systems, this dependence is much more exponential. So then you could have, let's say on the small scale, something which is very energy efficient, but if you need to pay a big overheads to scale that up to let's say high scale, where you have a lot of parameters, something of the level of very large models, you also need to think about the model, about the system considerations. And there is a lot of work that's being done in the memoristic technologies, how actually to address this problem. The another challenge is dealing with all the device non-linearities, because if you're using them as the analog devices, you cannot hide your imperfections with the digital abstraction. So then you really need to see how would this impact your algorithmic performance in terms, for example, inference accuracy. There's also the scope then to do a lot of optimization in terms of the materials. So again, this is just the snapshot of all the work that we did over years in optimizing the materials for the memoristic technology. So I don't have a time to go through all of these, but maybe for material scientists in the audience, you might recognize some of these figures. It's actually showing you some results, how the structure of the materials looks like, what happens when you bias them, what's the effect of the electric field, why does the oxygen move, how does it move, and so on. So you really need to understand the physics of the devices to have a meaningful way to optimize the performance. But then once you're done with that, you can also think about algorithms. So you have a lot of possibilities to be very specific about the ways how you optimize your algorithm specifically for this analog hardware. So this is an example that we did in our group about how to improve the accuracy, inference accuracy, both during the inference stage and also the training stage. So again, I don't have enough time to explain their approach, but basically you can read it in these papers. The point is that there is much you can do beyond just optimizing materials and devices once it comes to the system design. Okay, so I told you that this analog approach might bring you a few orders of magnitude improvements in terms of the energy efficiency, but how about going all the way to the energy efficiency of the brain? We still have many orders of magnitude of this gap. And there is a lot of talk what is called neuromorphic approach, actually trying to use some lessons or the things that we know about the brain and see if this is going to be beneficial if applied in our artificial systems. So it turns out to be that the oxide memristors, or memristors in general, could be quite useful to implement some of the basic functionalities of these biological systems. So that means synaptic functionalities, which is certain learning rules, and also how the neurons would behave. So generation of spikes and the information that we use for processing. But there's many other features of the brain we might want to use. So it's not only about the spike-based computing, so it could be also about asynchronous computing, computing with time, not in time, and so on. So this is a very active and multidisciplinary approach because we are learning about the brain as we go. There is many things we don't know about the brain, but what we do know, maybe it could be very useful to inspire us to design our artificial systems. We don't need to blindly mimic all the behaviors, but only those which are going to be computationally relevant. So again, this is the example of some of these functionalities that I mentioned. So on the left, you have actually spike time-dependent plasticity in the biological system. And then on the right, you have the same thing that can be implemented in memristors. Similarly, you can see how here in this example, you can use the memristors to generate some spikes. So that's you have these sort of two critical units, synapses and neurons, and from that you could potentially try to build your neuromorphic system. So to end with, there is many potential routes how the memoristic devices could be used and be useful for artificial intelligence. Anything from actually using them as a very efficient digital memory to these engines that operate with the concept of in-memory computing, also analog engines, also spiky neural networks, even beyond that. So again, not enough time, but I invite you to maybe read this review article that introduces some of these concepts. And then in general, how the future of computing might look like. I mean, nobody really knows, but we are hearing a lot about different approaches. So quantum technologies, of course, are very relevant. My personal belief is that all of these technologies are going to coexist. I don't think it's possibly, at least at the beginning, it's not going to be one single technology is going to overtake all of them. I think all of them could find their unique space where they could provide some benefits. So with that, I would just like to thank the whole team. This is the team at UCL that have been working on this, and also the research councils and the academy that sponsored the research. And with that, I would like to thank you very much and to open presentation to any questions you might have. Yeah, it's a bit hard to know what to comment on. I would say this is actually just in general a very exciting time to be a hardware engineer. We had this paradigm doing digital logic with the Moore's law for a very long period of time. And then basically we had basic principles of designing our hardware really fixed and set up. And we leveraged on that for 5 decades. But now is actually the time with this paradigm shift in how we do the information processing and in general, how we do computing to rethink on the fundamental level, actually, how do we do some of this stuff. Going from the fundamental technologies, so thinking about the materials, about the basic building blocks, such as transistors and memristors, and maybe some other technologies, to then thinking about the system design and algorithms. So very exciting time. Okay, so we have one question about learning a bit more about the topic and without the background in EEE. And any good textbooks for beginners. So it's a good question, but really hard question to answer, because the whole area of this research is really multidisciplinary. So you could really approach it from just learning more about machine learning in general. So thinking about artificial neural networks, of course, that's the main paradigm today. And yeah, it's very useful to understand that. Then also to think about at least on the higher level, how the computers work. Right. So what are the basic building blocks, how the information is processed. And then on the third level, you have the whole talk about the signal processing. So thinking about how do we process information beyond maybe Boolean logic, if this could be applied for some of these kind of applications and so on. So I wouldn't be able to recommend any specific book, but I sort of try to break it down into 3 separate topics. And I mean, even beyond books, there is a lot of available material out there that sort of from lectures, videos, that always helps. So I think we might have, is it another?
Adnan, there are 2 questions in the chat. So if I just ask you the first one, this is from Freya. Do you think the use of memristors will be able to become a national or internationally used way of increasing energy efficiency?
Okay, so if I understand, the question in general, just if you are able to produce more energy efficient hardware, it's going to have the impact for us all. So, I mean, any development in the new iPhone impacts everybody who uses it. So yeah, this is something that's not only going to be restricted to some national remit. It's going to have wide range impact.
Okay, and then the next question by Erkam. Before we finalize, I'd like to ask if there is any ongoing project where the output can be applied to robotics.
Yeah, absolutely. I mean, this is the whole area in general where the autonomous systems and AI merge. So you can think, okay, there's all the traditional methods that you would use to do this, but then applying AI and doing that energy efficiently, this very relevant and important because obviously when you have robots, they are mobile objects. You might have some batteries, and everything you can do to cut the power consumption is going to be good. I just now saw that you meant the project in UCL. Yeah, I mean, it's the best idea if you drop me an email, and then we can discuss specifically about the projects that might be available.
There's another question by Jamie. You talked about scaling up memristor technology. How many memristors do the best devices contain currently, and what are the main challenges to improving this?
Sure. So as I said, there is more than one way to use memristors. So if you talk about the memory, just the digital memory, then again, the picture is a bit more complex. If you're thinking about using this as some embedded memory for microcontrollers, you might think of megabits of memory. That might be fine. If you're thinking about using them as the storage memory, there's going to be gigabits and terabits. So currently, memristors as a digital memory are mostly used to have like a megabit capacity and apply for the microcontrollers. You do actually have a couple of products out there based on the memristor technologies, again, in the remit of the microcontrollers. In terms of the AI application, so that's still pretty much in development. And maybe the best way to think about this would be then to think about the size of your models, right? So if you have your artificial neural network, the size of such a model is going to influence what is the choice, how many memristors you need, or how many of these programmable parameters you would need to have.
I think we've got time for a final question, Adnan. So that's this from Ava. Do you think AI will eventually integrate into our daily lives as a way to control our own energy usage?
Right. So that's a very good question, a bit beyond my pay grade. But in a sense, yeah, it's a very good question, because I think we currently already have that. I mean, all of us are using these sort of trackers that are sort of tracking and controlling our activities. So that's sort of related to energy usage. If you think about our personal energy usage as how active we are. But if you think in terms of, I don't know, how much energy is consumed for heating or cooling or something like that, that exists as well. Yes, I mean, I think that's already implemented, but yeah, it could be pushed further for sure. And yeah, I would imagine there are many companies that are working on tracking, I don't know, food consumption or energy usage or something like that. I could see a lot of marketing opportunities for such a technology.
Okay, great. Thank you so much, Adnan. So I think we've come to the end of the lecture and the end of the Q&A session. Thank you all for joining us. I've popped Adnan's email in the chat. So some of you had some further questions. Do feel free to make contact. And thank you, Adnan.
Absolutely. Thank you, Nafta. And thank you all. Please feel free to drop me an email. We can discuss further.